That's how it's done. Cool. Okay. So then dig this, guys, for 7.5. We have, now we're getting past ellipses into something related called hyperbolas. It's another conic section deal. Hyperbolas. Cool. All right. With hyperbolas, the idea is kind of freaky. It's, I guess you could say it's like this. To motivate it, here, check this out. Okay. What if we were like circle, ellipse, and then we'll get it, whoa, now, ellipse, and then we'll get into hyperbola over here. What we know about circle is this idea that it's a fixed radius, so it's like you, once you picked a dot to focus on, we call it the center dot, then we just say, well, I'm going to try a fixed distance and find all the points that are a fixed distance away from it that are the same distance away from that. And that's whatever. It's pretty cool, I guess. And it doesn't matter which direction you look. It's like it's always the same bike spoke distance there or there or there. It doesn't really matter where you're looking, you know? It's almost like world peace symbol there, you know? But it's just sideways looking. Now it's just more like bike spokes. I don't know, whatever. And so then dig this. Oh yeah, so with an ellipse, we had a different kind of a construction. If you checked out Adam's take, we had this idea that, okay, we would start with a center point in mind, but then we would use two foci or two focuses. And then the trek would be constructed by us saying, well, if I had a string, that was a string of a fixed length, you know, like picture an actual string and say it was always 10 steps, you know, instead of it being like a radius of 5 on a circle. See, a 5 on a circle would be that if you staked it, if you put a stake in the ground at the center, stepped 5 steps out and wrapped that stake, you know, wrapped the string around a stake there, and then came back another 5 steps and then wrapped it again in the middle. What you'd have is 5 steps out and then 5 steps back. And then you got yourself a circle of radius 5, but it doesn't matter which direction you go. It's 5 steps out and 5 steps back, 5 out and 5 back, 5 out and 5 back, you know, and it's always just this 5 radius everywhere you go. If I were to take that same 10-foot string, which is 5 steps out and 5 steps back, but this time, instead of always going out some direction and then coming back to the same point, now with an ellipse, what we've constructed is, what if I staked my string to the ground, I went out however far I wanted to, staked it down, and then came back to this other point every time, you know? All in all, we still know it's a 10-step string. It's this 10-foot string. So maybe if I went right to the middle, if I had this thing staked to both of those focus points, as far as I'm going to be able to make it, would be just to have 5 steps out and 5 steps back. And it's starting to make, you know, and you could do that down here too, 5 out and 5 back, it's whatever. And then you're like, well, okay, what did that do? I don't know. But then you're like, well, that's not the only way. If I had the string staked to both of these foci, I could also be like, well, what if I wanted to like step out this way, you know, and just go a different direction? And, you know, we're starting to find like different points that are going to be on the ellipse here. There's one here and one there. And now we're like, well, the thing is, if I go out away from the other stake here, you know, then I'm noticing that the string is limiting how far I can go because I'm still tethered to the other one, you know, and so I can only go a little ways, you know, out to the left here before I'm tethered, because together they still add up to only a 10-foot string. And so we're like, well, I don't know what's going on, you know, maybe I went 2 feet on there and then this was 8 feet or something, or 3 and 7 or something. It's weird. Nonetheless, we found another dot where we could reach that string as far as it'll go if I'm stuck to both of those points, you know. So I'm stuck to both of these focus points and I'm wondering how far out I can go. And if you just keep on trying that, you'd be like, well, I could walk out this way and then I'm stuck because I'm tethered over there. I could walk out this way and I'm stuck because I'm tethered over there. And I could walk out this way and I'm, well, maybe not that far, but pretty close to that far. I could walk out this way and I get pretty far, but I'm stuck then because I'm tethered over here. And I could walk out this way, but I'm stuck. And the same thing, you could even walk just straight out to the left as far as you wanted, but you only get as far as that because you're stuck to the other pole. Same thing over here. And what you end up seeing, guys, is that there's still sort of a circular pattern to it. It's just that it's been squashed, you know. You can make it left and right a little ways, but when you go up and down, we're stuck at splitting the difference at half and half. And so what we end up with here is an ellipse. So an ellipse, we say, is, maybe you could view it in that construction as being like, well, I have these two focus points, you know, and the farther I stretch them out to the left and right, the farther out my circle gets stretched to the left and right, you know? And so that's pretty cool, Adam, huh? Okay. Now, hyperbola is going to be a whole other twist on this same kind of geometry, but this is what I wanted to do with you guys today, related to all that. Check this out. With a circle, we know that the way it goes is like x squared plus y squared equals some radius squared. We'll say 5 squared or something, you know, if that's centered at the origin. Whereas on an ellipse, we know that it's like when we have x squared and y squared, it's like we have to be able to account for the fact that this is stretching left and right more than it is up and down. And so if I had something like this, we have a lot of like math we can do about how far does it go up and how far does it go over and stuff like that. I guess I could figure this one out if I wanted to. Hopefully it's a 3, 4, 5. I don't really know. Maybe I didn't give enough info about it because we don't know how far foci are apart. However, we could say something like this where we'd be like, well, what would be the best way to think of it? Yes, let's do that. Okay, in this case, I have the x's are being stretched out further and further that way, you know? And so what we would say is if the x's are stretched out, then we have these numbers that are dividing under there. And as you guys might remember, when I have a bigger number under the y, it's stretching the y-axis further. If I had the bigger number under the x, then it stretches the x-axis further, because these numbers that are underneath there, they tell us how far we need to stretch these, the circle in each direction, you know? And so we'd be like, well, a 4, that tells me, you know, because the whole 2 squared thing, that tells me I'm only going 2 steps in each direction on the x part. And then the 9 tells me I'm only going 3 steps in each direction on the up and down part, or the y part. So this is what I wanted you to picture. If I had some x, and so, you know, we'll put number and some other number or whatever. Dig this though, dig. Before I get into hyperbolas, dig this. What if we said this? What if we had an ellipse and we're like x squared and y squared, not worrying about the new 0 thing, that just changes the center of it. And we're like equals 1. And what if I took one of those and I was like, you know, this just kept on being 9, say, or something, some nice number. And then the y part kept on getting huger, and we're like 100 or something. And we're like x squared over 9, and then y squared over 10,000, you know, and then x squared over 9, and then you're like plus y squared over trillion. And we'd have to kind of figure out how that's going to behave, but you kind of get the feel for it, because in each case, the x part is only going over a few steps, you know. We're like 9. If I think about square roots, we'll say call it 3 squared, you know. And then 100, that's a lot bigger than 9. So we'll expect this to go a lot further. But 100, still, if I think of it in terms of square roots, we'll say call it 10 squared. And so we're looking at this and we're thinking about it and we're like, well, okay, I got the center is at the center, it's whatever. But then if we were to try and figure out where to go with this thing, we'd say, well, the x part is like 3 squared. So 3 in each direction, 1, 2, 3, 1, 2, 3. And then the y part, though, is like 10 steps in each direction. 1, 2, 3, 4, 5, 6, 7, 8. I got this thing in the way there. Okay. 9, 10. 1. And then the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Way bigger in the y part, you know. And that's probably not news. Oh no, I'm doing something I didn't mean to do. Okay. Because that's sort of what we were just dealing with a minute ago. But here's where I wanted to go with it. Okay. X squared over 9, y squared over 10,000, we could say call it, 3 squared, and then call it 100 squared. And then it gets even worse, on the next one, it's like, well, okay, 1, 2, 3, 1, 2, 3. That's neither here nor there. That's not changing. But as the y squared gets bigger, the y squared dilation gets bigger, what you're seeing is this ellipse that is bending in left and or up and down. Oh, man, it's not even matching. There we go. It's going just way far up and down, without a whole lot of curving in anymore, So like you pull it out just a little bit left and right, and then there's a whole lot of stretch upward. And so what I wanted you guys to notice was this, though. When we go to extremes on something like this one, what we get is to the point where at some point it's so ridiculous. We still have a 9, so we'll call it 3 squared. So a 1, 2, 3, and 1, 2, 3. We'll call it 3 squared. But you notice that the square root of a billion or whatever this is going to be gigantic at some point. And so at some point, you're actually getting so huge that you go forever before you see this thing even start to turn in any noticeable amount, And so this thing is just going and going and going. And you're like, I guess I know that at some point it's going to turn in. But what I see is almost straight lines, and that we just know that as it goes up and up and up, eventually at some point it's going to eventually kind of curve in. But really right now it almost just looks like parallel lines because it's gotten to be so ridiculously stretched out on the y part. And I guess this is where we get into some weird territory, because check this out. So we're like huge on the y part. It's hugely stretched on the y part. And what we're noticing about that is that it's almost straight lines. Almost straight. I have too many humps in the eye there. There you go. Almost straight lines there. Because you have to go so far before it ever curves in, And so that's interesting. Because now we'd be like, well, that's almost straight. When you put a million or a billion down here, it's almost straight lines. And I'm thinking of a number, sort of, that's so big, that's like the biggest number, period, that would be so big that not only is it almost straight lines, maybe it's exactly straight lines. And so now we're like, now, what if we had x squared over 9 again? And then we were like y squared over. And then, guys, what number am I thinking of? It's the biggest number that you can think of, and it's not really a number.
Infinity?
Yeah, I'm thinking of infinity, like forever big. So we're like, well, what if I did this? This is not mathematically proper because it's not really a number and we can't really attain it. But I think, like, if we got that big, then we'd be like, well, I got 1, 2, 3, 1, 2, 3. And then you'd have to go out to infinity before this thing ever started, like before it ever actually met up there. You'd have to go, you go 3 steps left and 3 steps right. But then it's like you're up to, and you have to keep on going until you somehow hit infinity before you can come in. And that's not going to happen. And so you got 1, 2, 3, 1, 2, 3. And then over here, we're just dealing with like, well, I'll just keep on looking for infinity before it goes anywhere. At some point, It is just straight lines. At this point, it becomes straight lines. Straight. They never actually, straight parallel lines, they never actually curve in. And there's more that you could say about that too, because if you solve this equation out, essentially we're looking at the lines y equals 3 and y equals or x equals 3 and -3. Whatever. Notice this about it though. If I keep getting a bigger and bigger number in the denominator, something we've talked about in the past though, guys, is if you, maybe you don't have to write this part down, but if we keep getting a bigger and bigger and bigger number in the denominator, what seems to keep happening to the fraction is that the fraction is actually vanishing. Like if I were to forget about the number y in order to just put some number there, like 1 or something, or 5 or whatever, 1 out of, here, I know we've talked about this before, but since it's a weird thing, 1 out of 1 is a whole number. 1 out of 10, if I keep on growing the denominator, 1 out of 10 is a small fraction. That's a 1 out of 10 pieces of pizza, you know, it's like, it's sort of a decent sized piece. But then 1 out of 100, that's where the pizza pieces are so small it's getting to be insulting. And then 1 out of 1,000, that's what we've talked about in the past. It's like, yeah, I'm eating the pizza, I guess, but it's sort of an April Fool's pizza because I'm getting to lick the grease off the box. A 1/1000th of a pizza is nothing, you know. And then as it keeps getting bigger, one piece out of a million or out of a billion or a trillion is basically nothing. Nothing. So at the same time as what we're noticing about the up and down radius part is that as the numbers on the bottom of the y part keep on getting huger, what it means in the picture is that they're straightening out. It's basically straight. But what it means in number land is that, I guess you would just say in number land, that means that we're basically going to 0 here. And so if we were to consider what happens when we actually hit 0, or when we actually hit infinity, when our numbers get so big that they're actually the biggest ever, then two things happen. The picture gives us straight lines. The fraction, y squared over infinity, is essentially 0 at that point, because the denominator has gotten so big, so now infinity big, that now instead of having one piece out of a million where you're like, well, this is almost no pizza at all, when you get to infinity, it's so big that your pizza is actually nothing. You know, it's not just almost nothing, like 1 out of a million. It's actually nothing, you know? And so, and this is interesting to me because it leads us exactly where we need to go. Here's where we need to go, into hyperbola land. And I know we've gotten far out, so I'm going to rein us back in because I know it's gotten a little bit out in the left field. Notice this. If we had, so it's like x squared over 9 plus 0 plus nothing. Nothing, oh well, whatever, it's just nothing. Plus 0, that's a 0, equals 1, you know? And we're essentially not contributing anything to the y part, you know? And this is what I wanted you guys to notice. As the bottom number got so bigger, and it straightened out the lines to be totally parallel, and we were like, you have to go out to infinity before it closes in. The same thing that also happened is that the value of the entire fraction became basically nothing, because something over infinity is 0 now. It's nothing. And here's what I wanted you to do with me. And if you've gotten too far out, like if this is too weird, I understand, and you know, we'll record it so you can get the intuition or whatever, but maybe this is a good time to tune back in if that got too far out for you, because this is where we're going. I want you to tell me this, guys. I'm thinking of some kind of a number, and this is what I know about it. if I were so small a fraction that I hit zero, you can't really get much smaller than zero, you know? There's nothing, except that you sort of can sometimes depending on the application. What kinds of numbers am I thinking of that are smaller than zero? What kind of number is smaller than zero or less than zero?
Like negative?
Yeah, maybe we're thinking of negatives here. And so I think that that's where we need to go. We've gotten to the place of now being like, okay, now we're crossing over the Jordan here. Now we're like, we've gotten to the place where it's like x squared over 9, and then it was plus y squared over some, number or whatever, whatever it was, 100 or something. And that was like this, And then we got to the place where it was so stretched out. It was like all stretched out, like x squared over 9, and then over a million, and it was like way stretched out, almost straight. And then finally we were like x squared over 9 plus y squared over infinity is basically x squared over 9 plus 0 equals 1 equals 1 equals 1, whatever. And then at that point, these things are the same thing. If I put it over infinity, that's the same thing. It's basically just being a 0. At that point, we're like, we got straight lines. The only other place to go, guys, is if I were to go further than just being as small as 0, the only place to go would be if I were somehow smaller than 0, I'd have to figure out where that picture is going to go. Like, where can we go beyond 0? And this is where I think we could go. So after 0, here's, I think, the next evolution. Here, I'll go ahead and make sure that we have space for it this time. X squared over 9 plus y squared over a million. X squared over 9 plus y squared over infinity, or x squared over 9 plus basically nothing. Cool. These are all equals 1. And then we know what those look like so far. If I have 1 over a million, then we have giant ellipse, almost straight, Here we'll go like, almost straight. And then if we have y squared over actually infinity, then it's like, that's exactly 0. And that's, we've gotten to the place of like, now 0 is how much it actually curves in, is 0 amount it curves in. And so now we'll be like, well, we've gotten so extreme now that the ellipse is basically, it's just straightened out. And the only place I can see to go where from there, guys, is this. Now we're in hyperbola land. Hyperbola. Whoops. Hyperbola land. In hyperbola land, that would be where we go so extreme that we're like x squared over 9, and then anything less than 0 would have to be a negative now. Y squared over some number. We'll do, 100 again or something. It doesn't really matter. But now it's a minus of y squared over 100. It's actually gone less than 0, and we're actually in negative land now, equals 1. And now we're like, well, I don't know exactly what that means, but I can only imagine by the picture that it's this. Notice what's happened with the picture is that we've gone from ellipses that were curving sort of in to at the extreme, and it was an ellipse that actually didn't curve in at all. And now, if we've gone more extreme than that, if we have gone so far we have negatives, the only other place to go would be an ellipse that's so far gone that it's actually curving out. So we've gone from curvy inny to straight to now curvy outy. That's what's going on when you put a negative on either the x part or the y part of one of these ellipses. It becomes such an extreme ellipse that it's actually curving out instead of in. I know that took me forever to get to that point. It was a little clunky along the way. But that's the intuition I wanted you guys to have, is because now we'll be able to attack these things. We'll have this idea that's saying like, well, we can approach this sort of like we would an ellipse. But now we'll just know that when we have a negative in there, one of the curvatures of the ellipse, either the sideways part or the up and down part, one of them will be backwardized. And we'll do it like, I don't know, some kind of weird thing. I used to work with this guy. He was the principal at Hesperia Christian School. Or he was the athletic director, actually. And he had this sort of a weird double jointedness, cool ability to, like, he could make his fingers just go like this, all of them, without pushing them. It was rad. Anyway, so picture Mr. Haig doing that. Anyway, this is where we're taking off from. Backward hands. Now, dig this. I wanted to show you guys a little bit of particulars. Okay, so now if we've gone too far out, now we're reining you back in. Here's what I want you guys to start doing. We're going to draw one of these things together, and it'll be okay. Check this out. We'll start with it centered. Actually, forget that. We're not starting at the center or nothing. We'll just make it wherever we want to go. And we're like x minus 5 squared over. And then, hey, why not? Let's do 9 again. We've been doing that forever. And then I want you to go minus. And then we'll go y minus 2 squared over, let's do something normal again. And it'll be like 49 or something, something kind of nice, square rootable, perfect square thing. Equals 1. And so now it's like, if you didn't know better, you'd say, well, this is just an ellipse all over again. And it sort of is. It's a transformation of an ellipse. It's such an extreme ellipse that the y part now is negative. And so we know that the y part has stretched so big up and down. It's stretched so big up and down that it is actually crossed over from being up and down parallel lines into being outward curve. And that's what's going on here. And so now we have that the y part is stretched so far that it's kind of peeling outward. So dig this. Now we'll say, let's see if we can draw this. Now, some of this stuff you'll need some coaching through, and some of this stuff you kind of know. So I'm going to ask you guys a little bit here and there. Tell me, guys. Hey, Nicole, I didn't even notice you were here. Welcome in there, Nicole.
Hi.
Yeah, right on, Nicole. Okay, let's see here. Maribel, you ready? I'm going to ask you something that probably you know. Maribel, you there?
Yeah, I'm here.
All right, Maribel, take me through a couple of things real quick. I'm looking at where to start this thing, the center of it. I got x minus 5 going on. What's the new 0?
5.
It is. It's 1, 2, 3, 4, 5. And then what's the new 0 on the y part?
2.
5, 2. So we got over 5 up 2. That's the center. You could put it as little crosshairs if you like, or just put a dot. Either way, it's whatever. That's the center of this thing. Very good. Very good. All right. Rafaela, you ready? Don't worry, you'll know this one too.
Okay.
She's going to know it. You'll see, guys. Okay, what do I call it? Instead of 9, I'll call it.
You square root it?
Yeah.
3?
Yes, that's right. We'll call it 3 squared. And then what's this one going to be called? I think maybe your sound cut out for a second there.
7 square root?
Yeah, 7 squared. There you go. It's almost, I was like, I think she said something. Anyway, yes, we'll call it 3 squared and we'll call it 7 squared. And so now, guys, this is where I'm going to take you guys into, this is how this looks in hyperbola land. In an ellipse, we would know that that's how far we go left and right, and that's how far we go up and down and what we've done. And it's sort of the same construction, the same ideas here, but it ends up, because we're bending this thing outward now, it has a different kind of a construction to it. So this is what I want you guys to do. We'll keep in mind those exact dots, the 3 and the 7, and we'll go ahead and mark them out. That the x part is 3, so 1, 2, 3 on the sideways, 1, 2, 3 sideways, and then the y part is 7, so 1, 2, 3, 4, 5, 6, 7 up, and then 1, 2, 3, 4, 5, 6, 7 down. We got all that going on. And if this were an ellipse and everything as if that were like a positive y plus 2, then this would be curving in. And we'd be like, well, okay, it's curving in with itself and it's good. But we know that that is actually a minus of y minus 2 squared. And so since that's a minus, that means that the big axis, the y-axis there, it doesn't actually matter that it's the bigger one, but the y-axis one has been stretched so big that it is not only up and straight, it has gone further than straight parallel lines. It's bending out. And this is how we're going to deal with that. I want you guys to do this with me. We have our little, parameters to work with. What I want you to do is we're going to create a box. It's probably the easiest way to do this geometrically. We create a box and we'll be like 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7. What I want you to do is create a box out of that by going over the 3 and as high as that 7 steps up, and then put a dot in the corner that does both of those things. That is to say, if we went over 3 and up 7, well, let's go over 3 and then up 7 from there. Pop, dot. Same thing over here. We'll go over 3 to the left and then 7 up from there. And then we'll do the same thing downstairs. We'll say, well, what if I went over 3 and then from there I went down 7, And if I went over 3 to the right and from there I went down 7, and we're creating this box thing going on. It's freaky, I know. This is Dr. Funkenstein. And this is what I want you guys to do from now. Now that we got that box drawn, we're actually going to draw a couple of, we call them asymptotes. You guys have dealt with asymptotes in before, but essentially there'll be little straight line guides that'll sort of help us to draw our hyperbola to get the curvature right, because these will be lines that eventually it follows. It starts out curvy and then it kind of straightens out, and eventually our hyperbola is going to follow those lines. So what I want you to do is draw a couple of diagonals with me. We'll do it in a different color. We'll draw a couple of diagonals from one corner across to the other, and we'll just do little ghost lines of them, going right through that center, and then just dot, ghost line it, and keep it straight, and then just keep going way past the dot, and then same thing. We're going to go way past it here, way past, but just keep it straight. And we'll do the same thing on the other diagonal, from corner to corner. Now we'll be like, let's connect the dots right through the center, and then onward we go. Steady as she does it. There you go. We're there, and you're like, well, I didn't really draw a hyperbola, and we're not done, but we're basically done. Because the last thing to do, now that we have that, is just to finally draw our actual hyperbola. And it goes like this. Essentially, guys, we're just going to fabricate a curve. And there's ways to do this more accurately, like if we wanted to find the focus or something, we'll talk about that in a bit. But for right now, we're going to be like, well, I want you just to say like, well, we'll start somewhere between the center and this. This is actually, I think, the focus dot. We don't know where the vertex is. It's somewhere between here, and we can figure that out. What I want you to do is just for right now, curve your line or your hyperbola such that it's coming in like it were a straight line that's following that diagonal. And then it just kind of goes in between the center and that focus dot, and then starts to approach the other straight line, and we're just kind of going approaching those straight lines. And then the same thing on the left hand side. You're kind of tracing the straight line here for a while, and you come in and curve around in between the center and the focus dot, and then you're like, and then we'll just curve it around, and then we'll start to approximate the other straight line. And that's how we do. So if we have a hyperbola like this, in which the y part is what's being minus, it's the y-axis that's gone so extreme that it's bending outward. So it'll be this kind, Ta-da! Anyway, I'm going to have you try this in just a second, but instant replay, what went on is, we were like, oh, it's over 9, we'll call it 3. Oh, it's over 49, we'll call it 7. We draw our dots at 3s and 7s, and then we made a box about it. And then once we made the box, we did our little asymptote lines, and then we just kind of traced them to make, we traced our little asymptote lines to make our funny little bendy hyperbola. Yay! Right. Now I'm gonna have you guys try one. And I'll go ahead and here, well, let's just go ahead and do that. Let's try one, guys. Let's go x plus 3 squared over 16 minus y minus 1 squared over 36 equals 1. Try that for a minute. I'm going to go ahead and pause the recording here and just see what you can do. Okay, so then dig this, guys. If we had x minus 3 and all that squared, let's see if I can move this. You guys, I don't think, see all these little weird toolbars that I see. It doesn't matter. Anyway, so we're looking at this. We're trying to draw it, you know, we're trying to get a feel for this thing. Take me through, what if we had, Alex, you ready? I'm going to ask you some things that you probably know already. Alexis Becerra.
I'm here.
Who's ready? Tell me about it. We got 16. What do I want to call it instead?
I believe it's 4 squared.
Yeah, we'll call that 4 squared. And then, of course, we'll call this what?
6 squared.
That's right. Cool. Got that. Now it's Ray's turn. You guys ready, Raymundo? Raymundo. Ray!
What's going on?
He's here. And so then, tell me, I need new zeros here. Before I can make use of 4 squared and 6 squared. What's the new 0 here on the x part? Some number plus 3 makes 0.
Minus 3.
Yeah, negative 3, 1, 2, 3. And then some number minus 1 makes 0 on the y part. What's the new 0 here? Yeah, it's just a 1. That's good. Right on, Ray. So we're at negative 3 and positive 1. There's our center, guys. And then from there, we're like, well, let's see what we could do, I guess, you know, or whatever. And so then, I can't remember anything about anything. Oh, yeah. Oh, yeah. Yeah, I remember now. Okay, so then Alex had taken us through 4 squared and 6 squared. So we're like, okay, I guess I know where to go there. And so we're going to draw that in. And we're like, well, 4 squared, that's 1, 2, 3, 4 steps on the x part. And 1, 2, 3, 4 steps on the other x part going backward. And then we're like, well, on the y part, it's 6 steps. So it's 1, 2, 3, 4, 5, 6 up. And it's 1, 2, well, it's a big step. 3, 4, 5, 6 down. And we're looking good. But instead of drawing an ellipse from there, I'm going to ask you guys for what the heck can I do to draw this thing more appropriately? Where should I go from there? Let's see here. Yanelli. I got these dots in Ellie. Whoops. And I'm wondering, where do I go to make other dots so I can start making that box? Yanelli?
Yeah.
All right. Where should I make the next dot?
I'm trying to remember.
She don't remember.
No,
That's all right. Somebody help Yanelli out. She don't remember. So help her out, guys. What can we do? Where's the next dot go? Where's one of the dots going to go? How do I find it?
You go 4 to the left or right, and then up.
Yeah, that's right. Good save. Cool. All right. We got Yanelli on the spot, and she wasn't ready. So you guys got to save her, and he sure did. And so now it was like, yeah, we went over and then up the 6 or whatever steps. Yes. And then we'll do that the same thing with all the other dots. And so we're like over there and then down. And then to the left and then down and to the left and up. And now we got all those dots just like you were telling me. Very good. Now we got the old box. What we don't got is the vertex or whatever. We can, again, we'll address that when we get the chance. But right now, we're going to be like, well, let's go ahead and get a rough drawing of this because we need to draw our little diagonals, our asymptotes. So then, guys, I think it would be something like this, right? We're like, connect the dots. La, 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 la. Connecting the dots. We're feeling good about it. I love it. And then it's drawing time. Now we'll just come in with the old drawing. Here, let's go blue. Okay. And it's like, follow the asymptotes. It doesn't matter if you start from the top or the bottom. And you're just almost tracing the line because an asymptote does approximate that line. And then you just swoop in somewhere between the edge and the center. You know, we call this the focus dot in the center. We'll swoop in somewhere between those two for now. And then swoop on out again. And the same thing down here. And then swoop in between them. Not quite to that edge one. And then swoop back out again. Boom. Shakalaka. All right, this is what I want you guys to do now. Tell me what's different about this one. Anybody on this? I want you to tell me what do you notice that's different about this thing? 1 minus 3 squared over, let's go 25, that's a good one. And then minus x plus 8 squared over 36 equals 1. Okay, done. Tell me, guys, what's something that you notice that's different about this one than some of the other ones we've been dealing with?
Starting with the y.
Yeah, indeed. That's what I was hoping you would notice, is that the y part is normal and the x part is what's being minused. And so oftentimes when it's that way, we'll start with the y because it looks more natural to have the minus second. But yeah, we have the different guy is being minus. It's the x's this time that are negative. So what I want you to notice is this. If you got x squared minus and then the minus is on the y squared, that means that you've gotten so big on the y-axis that it more than straightened out, and then the y-axis is bending outward. But in this case, if you have y squared and then the x squared, the x is the one being squared, then that means that it was stretched out so far left and right that eventually the x part got parallelized, and now it is being stretched up and down, stretched outward. So when you have a minus x squared, you have a hyperbola that's stretching on the x-axis so far that it is bending outward that way. And so maybe if you're a note taker, make yourself a note of that. If it's the y that's being minus, then it's this kind of hyperbola where it's on the y-axis, it looks like, you know. There you go. Although it does not look like a Y chromosome as much as an X chromosome. So that's interesting. Anyway, and then I feel like I'm making these pictures immeasurably worse. But I can't stop. Okay, there's always hope, right? And so then if you have the x part as being minus, then it's this sideways kind, you could say, you know. So, and if it's easy to think of it that way, then just think of it as like if it's a y is being minus, since y is up and down, it's an up and down hyperbola, you know, or x is being minus, it's this sideways hyperbola because it's x's, you know, or whatever. That's fine too. Anyway, that being the case, that's what we're going to go on here. The mechanics of drawing this are going to be identical. You'll just make a box and all that and make the little diagonals, but then the way that we'll connect them, we'll know that it's going to be a sideways kind. Ta-da! So then talk me through, guys. Anybody on this one, see if you can pipe in. What do I call it instead of 25? What should I call it?
5 squared.
Square root.
Yeah, call it 5 to the 2. And then call it 6 to the 2. That's good, good, good. So we got our y's and our x's. Just notice that the y guy is the one that's going first here. So, you know, like Raphael was telling us. And so when we're doing call it 5 squared, that's the y part because it goes with the y. So watch out for that. 1, 2, 3, 4, 5. Oh, wait. Oh, my goodness. SpongeBob. Guys, I forgot to do the new 0. So we'll call it that. But we got to 0 this thing. So that's, what is that, +3 and -8? So then we'll go find our center at +3, -1, 2, 3, 4, 5, 6, 7, 8. Boom. Okay, now we're doing the steps. And so we'll say call it 5, but remember, even though it's first, it's the y part. So it'll be part of the y deal. So we'll go up and down 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. And then on the x part, we're going 6s. So then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Cool. And then it's like, we're not going to do an ellipse because we know better. We're going to make a box out of it, even though it's kind of funnily drawn. I stretched it too far to the left. It's whatever. Anyway, we'll make a box out of it. Over yonder, over yonder, over yonder, and then over yonder, and then we're like doing the thing. Here, let's just same color is fine. We're drawing our diagonal like we do. Same old deal, rinse and repeat. Just maybe draw it better than that. And then from there, we're drawing our hyperbola. But remembering that since it's the x part that's being minused, it's the x-axis that got stretched until it was going inside out. So that means we're going to say follow it on the top and bottom and make it look like it was the x's that got stretched. Something like that, I guess, except it looks bad. Maybe yours should look better than that one. It looks really bad. Okay, I'm gonna have you guys try one real quick, and then probably we'll go on break and we'll talk more about this and some other stuff too. Okay. We're gonna give you a problem to try. X minus 4 squared over 7. See, no, not 7. Wouldn't that be a time to start with non-perfect squares? Okay, so let's just do something nicer. We'll do 25 like we do. That's nice. No, not nice. Let's do a y1 like we just did. That'd be good. Okay. Y minus 4. There you go. Okay. Minus, and then x plus 3 squared over 16. 11 it equals 1. Cool. Do I look cool now? All right. I'm going to pause this recording real quick. See what you guys can do. All right, this meeting is being recorded. Dig this. Okay, where's the old stylus? There you go. All right. Boom, boom. Okay, so then talk to me, guys. We got this thing going on. You know what this means? That's 5 squared. It's what, 4 squared? And then besides that, we got ourselves new zeros to consider. I guess if I were to do this, we'd be looking at, let's see here, on the y part, that's a minus 4. So just remember, that's the y part there. So when you're doing your center, hopefully I didn't mess that up on the last one, did I? Minus 8. Minus 3 is positive 3. I sure did. Oh my goodness, the y part was supposed to be there. Okay. How do we, there we go. It's all forgotten. Just pretend like, okay, here we go. There's a star there. Okay. Now it's all forgiven now. Thank you. Okay. We have y minus 4. It's positive 4 is the new 0, but that's a y thing, which I apparently forgot to do in the last problem, but that's a y thing. So remember, that's 1, 2, 3, 4 on the y part because it's a y new 0. And then x plus 3 gives you a negative 3. 1, 2, 3. That's the x new 0. It's weird to do y first, but whatever. I mean, we did it for slopes, right? And so then now we're there, and we're cooking with gas, and then we just got to do the steps. So the y steps is 5 squared. Call it 5 squared. So the up and down part is 1, 2, 3, 4, 5 dot. 1, 2, 3, 4, 5 dot. And then the x steps is 4. So 1, 2, 3, 4. And then 1, 2, 3, 4. And then we're just boxing now. So then making that box happen, we're like, oh, that's both the 4 and the 5. And then both the 4 and the 5 here. And the 4 and the 5. And the 4 and the 5. And we're doing all of it. And then you just draw your little diagonals. You don't have to draw them as a ghost line. Probably it'd be good to draw them a little bit straight. And then once we get our diagonals in there, our little asymptotes, then we can just draw our deal. So then, guys, only thing that's different about this one is just like that one we did a minute ago. Since it's the x that's being minused, that means it's the x-axis that got stretched so far that it went parallel, and then it went more than parallel. So this is actually this kind, where it's the x-axis that got stretched backwards, you know? So here we go. We'll come off of our asymptote, and then through here, and then back out the asymptote, and then we'll do the same thing on the bottom. Curve it around, whoops, and then it missed, and so we try again. Nope, and then we try again. Whatever. I don't see you guys drawing on the stylus. Gosh dang it. But if you did, you probably did better than this. There you go. That's pretty cool, I guess. All right. Here, let me pause this recording here, guys, and then I'm going to take your temperature and stuff. All right, back in action. Here we go. Other challenge that you might be given, I'm looking over your homework, guys, and especially because I don't have an atoms take yet, this would be beneficial for us to mention. In your homework, it'll say they want you to give an equation when they give you just a few points to deal with. You know, they say, well, we have a hyperbola. Give us an equation. And so give equation for the hyperbola. That is the wrong letter. Hyperbola. Just, okay, I skipped a letter. Just whatever. Okay. This is what they give you, though. They'll give you a center point. We know how that works at wherever. And we'll say, here, I'm looking at this. We'll do 3, 2. And then they'll give you a focus and a vertex. Focus at some other point. And see here, that'd be negative 2, 2. And then a vertex at wherever, you know, and then let's see here, we'll do negative 1, 2. And that's it, you know, and then from that, you just have to construct the rest of it. But it is given that it's a hyperbola, so at least we know the framework with which to start, you know. And so let's see what we can do. I would recommend, no matter what, with all these weird conics, just to start drawing whatever they give you, because that tends to be the key for unlocking the mystery. So now we have center at 3, 2. Let's find the center. 1, 2, 3, 1, 2. There's our center point. So we already know right off of that that we have new zeros at like something minus 3 and something minus 2. It'd be like an x minus 3 and y minus 2. And we'll talk more about that, but let's go and get our dots drawn. Okay, center there. Focus is at negative 2, 2. So you're like, well, you keep talking about a focus. I don't really know what it does. And so let's go ahead and figure out how to make use of that. And so focus is at negative 2, comma 2. And so that's going to be -2 and then up 2. So it's just as high up as the other one, but it's over there. And then the vertex is -1, 2. So it's -1 up 2. And that's a vertex. And what I want to do is I'll put C for center, F for focus, B for vertex. And then this is what I want you to notice, guys. A vertex. We know what vertices are in terms of conics. Like when we had a parabola, a vertex was the dot that where it turned around, you know. And the same thing if it was a sideways one, you know, is the place where it turned around. And it'll continue to be the case. A vertex is that with a hyperbola. We have these things that go like weird, like it's inside out ellipse. And the vertices are indeed still the places where it turns. And it was the truth. That was still the case when we had ellipses too. The vertices were the places where it turned around from going left to right or up to down. So if we keep that in mind, that'll tell us a little bit about this picture, because we know how hyperbolas work. It's a hyperbola. So it's either going to be like something like this, or maybe it'll be an uppy downy one, but it's got two pieces to it. We know that, two curvy little pieces to it. And a vertex, we know what that looks like. And this is what I want you to do, guys. A focus dot, just like in an ellipse, you know, in an ellipse, we used to have, there was a center, and then there would be the two things that we talked about earlier in the day about the foci, the two focus points. And it was something about a string or whatever, and we used those two focus dots to construct the different dots that would make up our ellipse, you know, whatever. Something about the distance being equal all the time, piece of string, whatever. It's whatever. Anyway, so the foci are these dots that are not actually on the edge or on the ellipse or on the hyperbola, but they're dots that are sort of, they act like a center in a way, and that they help us to shape where to put the dots that go on our ellipse, or in this case, will go on our hyperbola. So that's what we expect the focus to be. A vertex is a place where we'll actually be turning around, whether it be sideways or up and down. A vertex is a place that we actually hit, and a focus is a dot that we use, but is not actually part of the shape that we're trying to draw. If we remember that much, then it'll tell us about how to draw this thing. So check this out. If we have a vertex and a focus here, the way that works is the focus is on the inside of the vertex. And so we'll say, okay, I have the center, and here's the vertex, and the focus is on the inside. So that must mean that our vertex, or our hyperbola, is going left and right like this, because the focus is on the inside, just like when we were talking about parabolas. You guys might remember when we said last week it would be parabola has a focus on one side, and then the directrix or whatever was on the outside. Then there's a vertex in between, but the focus is always the inside. Same thing here. The focus is the inside of the curve, you know? And so when they're telling you this stuff, and they give you a vertex and a focus that are next to each other, then we get this idea that it's like, oh, that means it tells me where to draw this thing. My vertex is here, I'm turning from there, but I'm turning toward the focus, which means it's to the left, it must be on the inside. So my hyperbola must go out to the left here. Then what I want you guys to do is we'll say, oh, now that I get the feel for the picture of this, I'm going to get the other dots, because that's just the left-hand side. And we'll draw them on the right-hand side as well. And then we'll have basically the drawing, and there's just a little bit more to know before we put it into equation, you know? And so dig this, guys. We'll say, here's the center. We have a vertex and a focus. Now we're going to find a vertex and a focus over here, you know? And it'll be just like, you know, like the other one. And there's no formulas to this that you'd have to memorize. We're just going to mimic what we did on the left over on the right. So this is the center. Well, that means the center. It's in the middle. And so we'll just see how many steps over we needed to go to get to that vertex. Help me figure that out. Let's see here. The center was at 3, 2. Then the vertex was at, the vertex is at -1, 2. So that's it. How many steps is that from 3 over to -1? 1. Is that 4 steps to the left? That sounds about right.
Yes.
Okay, cool. All right, so we got 4 steps. So then we'll do our other vertex will be 4 steps the other way. 1, 2, 3, 4. Other vertex, 4 steps that way. And then you can get the other focus in the same way. That's just one more step, or 5 steps from the center. So we'll go 5 steps from the center that way, or one more step. And there's the other focus on the other side. And that'll be enough for us to get a rough drawing, even though we don't know everything about exactly where the box is and where the diagonals are and stuff, you know. But at least we get an idea here. So this is what I want you to notice. Okay, so we've drawn it. That's good. Drawn. Good. Now we'll notice something about this, guys. Notice that the drawing that we made is this kind. It's not the, you know, it's not the sidewaysy kind. It's the up-down kind. So tell me, anybody that happens to remember, tell me if it's the up and down kind, is it the y that's being minused, or is it the x squared that's being minused when we write the equation? Is it x squared minus y squared, or is it y squared minus x squared? Which one is being minused if it's up and down? Is it the y or is it the x?
The X.
I don't remember. So let's see. Oh, it's the y. We tried though, Raphael, Donatello, or Michelangelo.
That's good.
Yeah, you know, we should try. And so if we have this up and down kind, and so like, I mean, you can always refer back to your notes if it's hard for you to bend your mind around it. We had a note a little while back ago about that. And so if it's getting mixed up in your mind, guys, feel free just to look back and be like, oh, if it's minus y squared, that's the up and down one. So we're dealing with this kind, so it must be the y squared kind. You know, the y squared is the minus. Okay, as it were. So we have the up and down kind of, you know, whatever. It's the y-axis that's been bent from being inside to straight up and down y lines to being, you know, this, you know, stretched outward. So we will say, oh, what do I do? Just, you know what? There it is. Okay. So we'll say it's not that one. It's the other one. So it's this kind. It's the y squared is the minus one. So now that we know that, we can start constructing this thing. So we'll say, so we know how this goes. Something squared, and they're fractions, and we'll have it equal 1. That's the way it's always going to go. Something's being minused. And now we know that the y is being minused. And so we'll say it'll be x minus something, and y minus something squared, but the y part is being minus because it's an up and down hyperbola. Or I guess they're looking sideways, but it's been stretched on the y part. Anyway, it's flipped on the y-axis, inside out. And then I want you to notice the center here is at 3 and 2. We already drew it, but if sometimes referencing the numbers might help or whatever. So remember that goes. That's an x is 3 and the y is 2. So we'll say for that, that's new 0 time. So we'll say x take away 3 makes 3 the new 0. And x take away, y take away 2 makes positive 2 the new 0 for the y part. So we have that going. And now we're basically done. We just need to know what numbers underneath here to divide by, you know. Don't know what those are yet, but we'll figure them out. And that's where we're going to get into a little ABC trick. There's a more appropriate way to think of this geometrically, but I just am having trouble appreciating it. And so I'm going to take you through a perspective that works for me, and hopefully it'll work for you. We got to figure out what to put underneath the x squared and what to put underneath the y squared. All we got is all this info we got here and there. Now I want you to notice this with me. Here's what I got for you. Something that we already noticed is they get from the center to the vertex was, how many steps was that?
4.
It was 4 steps. So we'll say from the center to the vertex, I'm going to draw a little line here, and we'll put 4, as in 4 steps from center to vertex. You could do that on the right-hand side as well if you like, or just on the right-hand side. I'm just going to do it on the left. It'll be the same on both sides. And then we noticed also that it was 5 steps from the center to the focus. That was 5 steps from here to there, but I'm not going to draw a line there because it's already on top of the other one. But I want you to notice something with me. Something that's not obvious is that what I want you to do, guys, is just draw a fake line going straight up. We don't know how far to draw it, but so we're just going to draw in something and put a little question mark there for now. We don't know how many steps that is, but there's going to be a dot here somewhere. And that's going to help us to draw the box. There's going to be dot there somewhere, but it's question mark on steps because we don't know how many steps it is. But this is what I do know about it. That number of steps that it took to get to the focus, that is equivalent to the diagonal, to the hypotenuse side, connecting the center to that dot that goes straight up in the box. And that's a little bit weird about like, why is that the same dot as the other one and stuff, you know? And so there's some geometry in there that we're not actually covering, but this was the simplest way that I could make it work without just having you guys memorize formulas and have a drawing to go off of. That made sense to me as well, you know? And so what I want you to do is this, we'll say, okay, it's 4 steps to the vertex, then some number of steps up, but we don't know, but we'll figure it out. And then since it was 5 steps to the focus to get from the center to the focus, that's actually going to be equivalent to the number of steps that it takes to get through this hypotenuse. So I want you to put a 5 there, not because it's obvious, but because it matches the focal diameter there. And then once we're there, we're like, oh, it's over 4, it's up some amount, don't know. But that's a right angle because it's over and up and equals the 5 thing. Tell me, guys, if I have the 4 there and don't know there and then 5 there, how do I figure out the up part now that it's a triangle like that? What would you do if I sang out of tune? What do you guys think? How do I figure that out? Any ideas? Guys.
A squared plus B squared equals C squared, I think.
Yes. I knew you knew. The Smiths know. So that's actually, it's a good guess and it'll work 100% of the time. So what I want you guys to do is we'll just say, we'll take that to the side. We know that we're trying to figure out like what numbers go down here. It's not real obvious, but we're almost there. And so now we'll be like, oh, I can figure this out. Once I get the box there, then that'll tell me how many steps to go this way and that way. I'm almost there. And so we'll say, okay, 4 squared plus something squared. We'll just put x squared or don't know it's squared or b squared. Maybe we'll put b squared. I don't know, whatever. Equals 5 squared, you know. And we don't really know what this part is, question mark squared, you know, and we'll just run the numbers. That's what 16 plus b squared equals 25. And we're just kind of running them. 25 minus 16 is like 9. So then that means b must be equal to what, guys? What's it going to be? Something squared equals 9. What's b number equal?
3.
Yes, it's 3. So you got b equals 3. Loving it. And so then once you got that, feel free to fill in the blanks. And we'll be like, oh, that's a 3 there. Oh, 3. And that's enough to get us going on drawing the rest of the dots. Because now we have a framework for the box. We know we go over to get to the vertex 4, and then up 3. And that'll be enough to get all the dots, because all of the other triangles will be drawn the same way. It'll be over 4, then down 3. 1, 2, 3. Over 4, up 3. Over 4, down 3. And now we got ourselves a box. And from there, we could like draw the diagonals and get the asymptotes and draw this thing real well. But what that also tells us, guys, is I know how far left and right I need to go, and I know how far up and down I need to go. That's 4 steps to the left. We knew that that was 4 already because they sort of gave us that. So what I want you to do, guys, is remember, if I'm talking left and right movement, is that an X thing or a Y thing? If I'm talking sideways movement, is that X or is that Y?
X.
Yeah. So that's a 4 in the X direction. So what we'll say is down here for the X part, we'll say that's 4 squared. And then in the Y direction, we didn't know that at first, but now we figured it out. It's the up part is 3. So the Y part is 3 squared. And now we're done. Now we have our equation. Now we can just say, oh, I think I got it figured out. It was x minus 3 squared minus y minus 2 squared over 4 squared and 3 squared equals 1. Giddy up. Now that's a lot to take in all at once.
I have a question.
Yeah.
Where did you get the 5 at the end of the equation? 4 squared plus b squared.
Yes. That is not obvious. So yes, let's go ahead and give that some emphasis. When they give you these dots in the first place, the ones they gave you over here, and we drew them, we had first off a dot at the center, and then one at the focus, or sorry, the vertex, and then one at the focus. And if we notice how far apart they are, we knew it was 4 steps to get to the vertex. And if we look further, we can also notice that it is 5 steps to get from the center to the focus. 5 steps to get from the center to the focus. And so what I have done is there's a little smoke and mirrors about how and why this is the same distance or whatever, but that distance from the center to the focus is also going to be the equivalent to our diagonal distance here. And so however many steps they give you between the center and the focus, then you'll know that when you're drawing your little triangle over and then up, that we know the diagonal is exactly that same number of steps. And that's where I'm getting the 5 from, is because that is also the same number of steps from the center to the focus dot that they gave us.
Okay, thank you.
Yeah, did that answer anything at all?
Yeah, I did. I just didn't know where it came from. I get it now.
Cool. Right on. Now, this is a lot, like we were saying, to take in at once. So maybe let's try another one together. Okay, let's go center at, let's do 3, 6. Whoa, that's a backward comma. 3, 6. Focus at 8, 6. Vertex at -1, 6. And so again, I'd recommend just drawing it and seeing where it takes you. So we have to find the equation here. They give us a center at 3, 6. So we know where to draw that. That's 1, 2, 3, 1, 2, 3, 4, 5, 6. Boom. And then we got a focus somewhere and a vertex somewhere else. Let's see here. Focus is at 8, 6. So that's 1, 2, 3, 4, 5, 6, 7, 8, and then up 6. And then a vertex at -1. So let's see here, -1, 6. So they're all kind of sideways again. So it gives us the clue that even though we haven't really drawn it yet, it's probably going to be sideways this way. So it's going to be the y-axis that got split in half. So it looks like we'll probably have the y part being minus again. But let's go ahead and draw the rest of this stuff. And so this is what I want you to notice. They're drawing you a focus on one side of the center and a vertex on the other side. But we have both of those things on both sides. So let's just go ahead and see how many steps it takes to get there, and we'll draw them both. See, this is the center. We have a focus at 8, 6, so that's a focus. And then we'll have a vertex over here somewhere as well. And the same thing, this is a vertex, but we'll also have a focus over here somewhere. There's both on both sides. We don't know where these ones are yet, so we'll figure them out, you know. So this is what I want you to know. Remember, vertex, that's the place where we hit, and then the focus is on the inside. That's what's going on here. So we have to find a vertex that's somewhere like there, I guess. But the way we'll do it is not by just doing a lot of figuring. We'll just notice where the other vertex is. So here we go. How many steps is it from the center to the vertex? Somebody count that for me if you don't mind. We're at, what is this, +3? That's at, what, -1. So how many steps is it to the vertex here?
4.
Is it 4 again? Okay. So that's 4 steps to this vertex. So then our other vertex will also be 4 steps. So we're going to go, he was at 3. So, 3, so 4, 5, 6, 7. Here's the other vertex. And the same thing for the focus. We'll say the focus was way over here at 8. So these are similar numbers to last time, it looks like. Let's see. From the center to the focus was how many steps? 5? I guess 5 steps. So then our other focus will also be 5 steps away. So it'll be just 1 past the vertex. This is the same steps structure as last time. And once we're there, we kind of know how it goes. And since this is a vertex and that's a focus, we know it kind of bends around like that. And we know it kind of bends around like that. And now we just got to start drawing the thing. Since it is this kind, it's the y-axis that's been split in, inside out. We know that since it's that way, it's the minuses on the y squared, not the x squared part. So here we go. We'll get it ready. Something squared minus something squared. They're each over some number equals 1. Here we go. Keep that in mind. Oh, since it's the y that's being squared, or that's being minus, we'll just go ahead and do that. We'll put the y on the second part, and that's being minus, and the x is what we'll start with. Okay, so that's good. Because it's a side-to-side, up and down parabola, or however you want to say that. And then we got to find, oh yeah, so the center part, we know from new zeros here, the x part is 3 and the y part is 6. So then we'll just new zero it and be like, x take away that 3 and y take away that 6, each being squared. And now we're basically done. We just got to do a little geometry and we'll fill in the blanks down there about what numbers go there, And so that's where we'll have to draw a little bit of geometry in here. So here we go. Pick your favorite, doesn't matter where you draw it, but go ahead and connect the dots here from the center to the vertex and we'll notice how many steps that was. I believe that was 4 steps again this time. And then we'll say straight up, we know we're going to make a box here. We don't know how far up, so we'll leave it, but we don't know how far up, question mark, not sure. But once we got that, it'll be straight up, and then we're going to cut the diagonal and be like, well, however far that is, but we know how far that is because that's the same thing as the distance to the focus, which is how many steps this time, guys? How many steps to the
5?
focus? Yeah, it's 5 steps. So this is weird because these are the same numbers as we had last time. So it'll end up probably the same kind of thing. They do that because they want to be nice to you on numbers, probably, because, Pythagorean Theorem gets so ugly so fast. Anyway, and so from there, we'll be like, well, 4 squared plus something squared equals 5 squared, and then you play that same old game. 4 squared plus b squared equals 5 squared, and then you're playing it until you're ... b squared equals 9, and then square root it, b equals 3. And once you're there, that tells us the up part. So now we know that whether we're making the box up there or down there or over there, the box is set up of all these steps that are always 4 steps to the left and right and 3 steps to the up and down part. So then we'll say, oh, okay, I got it, except I can't read the 3 anymore. 3, 4, cool. And then those become the things. So then the 4 is the sideways part. So that's an x deal. So we'll go equals 4 squared. And the 3 is the up and down part. So that's the y part. So 3 squared. Ba, ba, da, da, ba. Eh? With the little bit of time that we have left, I think instead of trying to cram something in at you about systems of equations, which is maybe not as bad, let's have you practice this, which is as bad. And so, and then we'll probably be done. And so check this out. Try this real quick. See what you can do here, guys. I'm going to give you a center. And let's go for 5. A vertex. And a focus. Okay, let's see here. Let me fix this real quick. Let's go for 17, for 18. All right, see if you can come up with an equation for that. Take your time. I'll just be sitting back, sipping lemonade. Although it's not, still. There, Lupe, you still there?
Yeah, I'm here.
I noticed you put an L there. Is that because you actually do go by Lupe, or do you prefer to go by Guadalupe?
Oh, people that know me, or it doesn't really matter. Like, people that know me always call me Lupita because they know me, but
Yeah.
and in high school, I would always tell my teachers, like, oh, it's Lupita, but in college, I just stopped. So it doesn't matter. Guadalupe or Lupita is fine.
Lupita? We're doing
Yeah.
that. I love it.
I'm glad.
Until we can figure out a better nickname for you, something more embarrassing.
Please do.
Got it. We're on it. Guys, you heard. She has asked us to find a more embarrassing nickname. So whatever comes to mind. Oh, I forgot to pause the recording. Wouldn't this be a boring thing to watch? Recording. Okay. Take this, guys. Probably won't be able to get your input on this one because there's a minute and a half left. So here we go. We got a center at 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5. Hopefully you're getting that there. And then we're like vertex at 417. Great. Okay. So then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. No, 17. Oh, but the other thing is at 18. So we got this one is like that. It's got a center yonder, and then the focus and vertex are both upstairs. So then we'll have another focus and vertex downstairs. Let's see how many steps apart they are. How many steps is it from 5 to 17? That's like 12 steps, right? So then 12 steps and 13 steps. This is a vertex and a focus. So then we'll go 12 and 13 steps down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, and 13. Vertex Focus. Okay, so we got those going on. Since it's an up and down one like this, we know that it's like our hyperbola will draw that way as well. So that means if it's that kind, it'll be a minus on the x squared part. So we have y minus something squared and x minus something squared, but we're putting the x second this time because it's the one being minused. And we don't know the numbers underneath. We'll probably get it equal to 1. And so then let's see what we can do. The center is at 4, 5, so we can make that work. Let's see that, but be careful. The 5 is the y part, that 4 is the x part. Remember, I messed that up earlier. So the y goes with the 5, so it's y minus 5 and x minus 4, both being squared. And then I don't know anything. Yes, I do. Yes, I do. Check this out. What if it was this? And we were, oh, it's 10:55 already. So then we were like, oh, it's 12 steps to the vertex. And then some amount of steps going to the side because we're drawing the box here. We know the up and down part. We don't know the sideways part, so we'll draw a box going sideways. We don't know that part, but we know it's 12 steps here. We don't know how many steps sideways, but we know that the diagonal matches the distance to the focus, focal radius or something. And so then that was 13 steps, I believe, because it's just past the 12, so that'll be 13 here as well. And then we're playing the game with the Pythagorean Theorem, and we're like a squared plus 12 squared equals 13 squared. Or you could treat that as a b and be 12 squared plus b squared. It doesn't really matter. And then we got a squared equals, what's 169 minus 144? 25. So then a equals 5. Looking good. So we're like, oh, must be 5 steps here. Oh, 5. And if that's the case, we know the up and down part of the box, and we now know the left and right part of the box. So if we wanted to make all these dots for all these boxes, we could now. It's 12 steps up and down. It's 5 steps left and right. We could draw little diagonals and get an accurate drawing if we wanted to. It's whatever. But now we know that the up and down part is 12, so the y part is over 12 squared. And then we know that the left and right part is 5. So the x part, being the left and right part, is over 5 squared. And that's how the cookie bounces. Cool. Let me stop this recording here.